Okay, um, so we're now turning our attention to, you got glucose that gets inside your cells. We're not talking about insulin and glucagon and how glucose is transported into your cells. We could do that other than that I don't know it very well, so I'm gonna have to leave that for other classes that you might take. But what we want to talk about is the chemistry, really the what and the how and the why that enables a molecule glucose, which has 6 carbons, to first, in the process of glycolysis, be converted into 2 molecules that have 3 carbons each. So in glycolysis, we're going to break a glucose apart into 2 equal pieces. And in the process, we're going to make 2 molecules of ATP and 2 molecules of NADH. You've seen ATP before. It looks like this. And by the way, I am sorry, I prepare these handouts on my computer. If you've been to my office, I have this big screen, and so it looks bigger on the screen than it does on the page. I was looking at that as we printed it out, and I'm like, huh. And I brought it closer to my face, and then my old man eyes were making it blurry. So I'm hopeful you can see it. If you can't, just download it from Learning Suite and blow it up on your computer screen. It'll become a little bit clearer. I kind of wanted it to fit all on one page, but maybe that was excessive. In any case, we can zoom in here. So this is ATP. ATP is the chief energy currency in your body. The reason it works is because of these high energy level 1 reactivity electrophile phospho and hydride bonds. So this functional group where the phosphate, the gamma phosphate, which I'll highlight in blue, and the gamma oxygen are attached to what is essentially a phosphate leaving group. That's a level 1 electrophile. And ATP does the work in biology by transferring phosphate groups. This happens all over, and in particular in muscle movement. Muscle movement involves ATP transferring a phosphate group that introduces negative charge in a place that wasn't negatively charged before. Charge repulsion makes the protein move, and then the protein moves somewhere else, and then your actin moves along the myosin and so on, and your muscles are able to move. So you need a ton of ATP to live and breathe and think. Everything that you do is powered by that. And maybe we'll say more about that later. We'll also eventually do some math to figure out if the average human needs, the average well-fed American human needs anywhere around 2,000 calories a day, exactly how many molecules of ATP does that correspond to? And exactly how much glucose would you have to eat if that were your sole energy supply? And it's kind of interesting. The second molecule that comes out of glycolysis that's energy currency, in addition to ATP, and I'm going to put an explosion around ATP because it's an energy-rich molecule. The second one is NADH, and this one may be less familiar to you. Here is NADH. N stands for nicotinamide, which is this portion of the molecule. Unfortunately, this is the business end of the molecule. A stands for adenine. That's this portion of the molecule. D stands for dinucleotide, and that's this portion, this central portion of the molecule. You have 2 ribose rings, and they're linked together by a pyrophosphate linkage. For the most part, when we draw NADH or when we use it in mechanisms, we're going to draw it like this: an R group here, a nitrogen here, 2 double bonds here, and then an sp3 hybridized carbon here. And this is how we'll draw NADH. And it's important that you know that NADH is in its reduced form, and it is electron rich. NADH has an oxidized form called NAD+, and we'll just use an R group for NAD+. It'll look like this. In NAD+, the nitrogen, which used to have a lone pair on it, is now involved in a pi bond with the adjacent carbon, and therefore has a positive formal charge on it. In NAD+, we've lost a hydride, or an equivalent of H-. I'll highlight that here. This hydrogen and its 2 electrons are not present in NAD+. So NAD+ is oxidized and it is electron poor. One way to see this is to draw a resonance structure of NAD+ that looks more like NADH, but at the carbon that is opposite the nitrogen, there's a positive formal charge. You could get to that resonance structure simply by pushing the arrows like this. So NADH can receive hydrides. It can receive hydrogen and 2 electrons. It can receive a proton and 2 electrons. NADH can deliver a hydrogen and 2 electrons. Your body uses NADH and NAD+ to help catalyze a lot of reactions. For our purposes, though, NADH can be delivered to the electron transport chain in mitochondria, and there it delivers its electrons. Those electrons follow a path that ultimately end in reducing oxygen to water. That's why you breathe oxygen, to receive the electrons from NADH. But along that process of reducing oxygen to water, the electron transport chain drives what's called a proton gradient. It makes the pH inside the mitochondria higher than the pH outside the mitochondria, and because of that, flow of hydrogen back into the mitochondria through an enzyme drives ATP synthesis. So this is a well-oiled and very intricate machine with many parts. We're going to talk about the electron transport chain later, but before we get there, anytime you see NADH, you need to be thinking, I can exchange that for ATP in the mitochondria. And I forget what the exchange rate is. It's around 2.5 ATP per NADH. Don't hold me to that. I need to look that up, but I think it's about 2.5. Yeah, Myler says that's right? Okay, good. So we're going to talk more about this and how it works. You can use the ATP you make in glycolysis directly. The NADH you can use for a number of purposes, but if you can exchange it for ATP in mitochondria. The process of glycolysis happens in the cytosol, so not in the mitochondria. Once we split the glucose molecule into 2 3-carbon parts, those 2 molecules are both called pyruvate, 3 carbons. Both of them have to pass through something called the pyruvate dehydrogenase complex that removes one carbon from each pyruvate. There used to be 3 carbons in pyruvate. One from each of them get removed as CO2 with 1 carbon, and then the remaining molecule is the thioester acetyl-CoA, which only has 2 carbons. So in the process of glycolysis and then going from the pyruvate dehydrogenase complex, you go from 6 carbons down to 4. And 2 of the carbons from glucose you exhale as CO2. The CO2 dissolves in your blood, and then it comes and is exchanged for oxygen in the lungs, and then you breathe it out. Okay, questions about that overview? At some point, I'm going to ask you a question about how many ATP you get out of this process. So let's look at what you get up through glycolysis and the citric acid cycle from 1 molecule of glucose. All right, I count overall. Oh, shoot. We need to amend your list because I left something off it that's important. And that is, this should have said NADH. So the pyruvate dehydrogenase complex takes 2 pyruvate, generates 2 CO2, 2 NADH, and 2 acetyl-CoA. I'm sorry about that. I will edit that and post a new one. And if you want, I will print it out again, and then you can have a fresh copy that's correct. Or you can just scribble it out and correct it. All right. So let's see what the overall yield is for 1 molecule of glucose. We get 2 molecules of ATP out, and then overall, up through going to acetyl-CoA, we get 4 molecules of NADH times 2.5 ATP per molecule of NADH. That is, oh brother, 4 times 2.5, that's 10. So overall, from glucose through acetyl-CoA, we get 12 ATP. TAs, you want to check that? Does that sound roughly-ish okay? I'll look it up again, see if I did something wrong. Yeah, okay. Now understand we're not done there yet because acetyl-CoA still has 2 carbons in it. We still need to oxidize both of those to CO2. This carbon in acetyl-CoA has 3 bonds to a heteroatom, CO2 has 4. So that's got to get oxidized, and then the methyl also has to get oxidized. There's a lot more chemistry to be done. That happens in mitochondria in something called the citric acid cycle. So we're going to learn about that too. I don't yet know whether we're going to get through all of that or even any of it before the next exam. So we'll just play it by ear as we go along. But understand that we are going to add many more ATP molecules to our tally from a single molecule of glucose. Go ahead.
Where does the 4 NADH come from?
2 of them come from glycolysis, and the other 2 come from the pyruvate dehydrogenase complex. Yep. All right, others? Yeah.
Where's the 2.5?
So in the electron transport chain in mitochondria, NADH can be exchanged for about 2.5 molecules of ATP. We're going to learn about that. We're not learning about it yet. But basically, NADH delivers its electrons to the electron transport chain. Those funnel down through an elaborate pathway to reduce molecular oxygen to water. In the process, enzymes in the electron transport chain pump hydrogen atoms, or rather pump protons, H+, across the mitochondrial membrane. That creates a concentration difference between sides, and to equal that out, hydrogen ions actually flow through something called an ATP synthase, and they provide mechanical energy to make ATP. All right. So that's our overview. Now let's focus first on what and why. Then we'll worry about how as things go on. So the whole process from glucose to acetyl-CoA is listed here. Glycolysis includes everything from this dotted line to this dotted line. Then the next thing is what happens to pyruvate, which is it gets converted to acetyl-CoA. That's the pyruvate dehydrogenase complex. That is not considered part of glycolysis. It's rather the bridge to the citric acid cycle. So we start with glucose, and we end up with glucose 6-phosphate. So in glucose 6-phosphate, you have the phosphate group attached to the C6, what used to be the C6 hydroxyl of glucose. What is that functional group? It's phospho something. Is it phospho ester because it's attached to what used to be an alcohol? Great. And here is the alcohol that it used to be attached to. The electrophile, the alcohol is the nucleophile. The electrophile is ATP. You've seen ATP before, and you've seen that the gamma phospho group from ATP is involved in a phosphoanhydride bond. So I'm just going to highlight that here. ATP is a phosphoanhydride. That's a level 1 electrophile, and it becomes now a level 2 electrophile after the reaction. And it's the gamma phosphate from ATP that gets transferred to glucose. The enzyme that does this is called hexokinase. The name kinase, these enzymes are always involved of transfer of phosphate groups either to or from ATP. So if you see an enzyme and it's named a kinase, either to ADP or from ATP. If you see the name kinase, you need to be thinking, I'm going to break a phosphoanhydride bond and make a phosphoester, or vice versa. Okay, now I want you to look at maybe the second question on your quiz. We've talked about what happens for this step. Based on what you learned last week for mechanisms, I want you to work your way through the arrow pushing mechanism for this reaction. You have in front of you the structure of glucose, the structure of ATP. You can figure out the structure of ADP. You have the structure of glucose 6-phosphate. And you've learned about nucleophiles attacking electrophiles. So I'd like to see what you can come up with at this point, drawing a mechanism for this first step of glycolysis. Along the way, please feel free to abbreviate the structure of ATP as needed. For example, you could consider drawing it like this, in which you draw just the phosphoanhydride bond between the gamma and the beta carbons, and you leave everything else as an OR group. That's one way you could consider drawing ATP. Also, feel free to use a base from the enzyme. A lot of these groups are actually known, but we're not going to worry about them. So that ends with a B with a lone pair on it would be a basic group. Ends with an A and then an H on it, that would be an acidic group. Feel free to use those for proton transfers as needed. And feel free to include proton transfers with nucleophilic attack or elimination steps as needed to make the mechanism more abbreviated. All right, with that, go. I will give you, I think this may take a little bit of time, so I'll give you 4 or 5 minutes on it, and I'll wander around answering questions if you have them. Then we'll talk through it. let's talk through it. And you can draw glucose in the chair form, or you can draw it in this overhead form, doesn't matter. You prefer the chair?
No, I was just asking you
Oh, you can totally do the chair. Yep. Yep, drawing it in the chair form is always fine. Drawing it overhead is always fine. All right. So, as I said, your OH group is going to be your nucleophile, and then ATP is going to be your electrophile. We identified in ATP the key functional group is the phosphoanhydride bond between the alpha, nope, I got that wrong, between the gamma and the beta phosphoryl groups. So with respect to ATP, this gamma phosphate is the electrophilic atom, and you're going to treat the phosphoryl group just like a carbonyl. That is, you're going to think about all of this as being the leaving group, and that leaving group is really just ADP. So the pattern we've seen before is we're going to use a basic group to deprotonate the alcohol. Then the negatively charged alcohol, we could draw at this stage, we could go like this and draw a negatively charged alcohol intermediate. If you did that, no problem. That's totally fine. In fact, I used to prefer that, but it's a lot of drawing. So if you want to do it this way, it's fine. You deprotonate the negatively charged the alcohol, then the negatively charged oxygen attacks the phosphorus. We okay there? Okay. That makes sense because if you look at where we need to end up, the oxygen is now bonded to the phosphorus, right? However, what we do next is sometimes tricky. I've seen a couple of different things as I've been wandering around. One of the things I saw was sort of a direct substitution step. That makes a decent amount of sense, and that's actually the way some textbooks show it. But there's actually evidence that phosphoryl groups are very much like carbonyl groups. So you're going to attack basically the phosphorus oxygen pi star and break the phosphorus bond. Yep. So that is an addition step. So for phosphoryl chemistry, rather than doing direct substitution, you're going to do addition plus elimination. At this stage, I draw the intermediate in which phosphorus is bonded to 5 different things. One thing that you should know is there's a lot of negative charge here, and most of the enzymes that are called kinases have a magnesium cofactor that helps mediate the negative charge. We won't always draw that, and you may forget it, but often magnesium is necessary to help stabilize that intermediate where there's so much negative charge. Now, I'm already drawing it wrong because I was talking while I was drawing. This is the gamma phosphate group. This is the beta phosphate group. This is the oxygen from glucose. I'm now going to abbreviate glucose as just R to make our drawing simpler. Then electrons on one of the negatively charged oxygens, actually doesn't matter which, kick down and kick off the leaving group, and that's the elimination step. When you do that, you have your new phosphoester, which I'm abbreviating like this. This is glucose 6-phosphate. And then your leaving group is ADP. And you are welcome to abbreviate that as well. Alternatively, if you want to see what it looks like, This is the beta phosphorus. This is the alpha phosphorus. This oxygen here is the C5 oxygen from ribose, and then the base A for adenine is there. This is ADP, and that was the leaving group. Okay? Yes, go ahead.
For direct substitution, would it just skip the addition and elimination step?
Yeah, if it proceeded via direct substitution, you would draw this arrow and the leaving group would leave.
But isn't that the same thing as addition and elimination?
It gives you the same products, but it's a different pathway.
So how can you tell if it is supposed to be elimination?
There is the direct $6 million question. What evidence is there that you add to get an intermediate and then elimination occurs, as opposed to adding and eliminating at exactly the same time? Great question, and that gets into, there are experiments called kinetic experiments that investigate mechanisms, and you can change the concentrations of various starting materials and intermediates and see how that affects the rate, and you can sometimes infer as a result whether what the mechanism is. You can also look at the enzyme active site, and you can put molecules in it that resemble this and see whether they fit, and those are some of the ways you can try to tease it out.
So could we use the two interchangeably?
Can you use direct substitution versus addition plus elimination interchangeably? No. I'd like you to use this, even though it's faster, it's less realistic, and it matters especially for carbonyl groups. Carbonyl groups don't do direct substitution. All right, I saw a bunch of other hands. Go ahead.
Do you want us to reprotonate the ADP?
Do you need to deprotonate the ADP? You certainly can. I usually forget and don't bother. The reason I don't bother is because this is a reasonable form at pH 7. The dianion and the monoanion are 1-to-1 at pH 7.5, so it's fine. Either way. Other details? Yes?
Can you explain
Why
why the lone pair on the oxygen attacks the phosphate?
the lone pair? This step?
No,
This step.
yeah.
Okay. So the alcohol oxygen is nucleophilic because it gets deprotonated and has extra electron density. The phosphorus is electron poor because it's attached to a good leaving group. So you can think of ATP in the same way that you've thought of carbonyl compounds that look like this. Good leaving group, electron poor atom, and atom that can receive the electrons after the attack.
So it's kind of that pattern of leaving group, and then the receiving group, I guess.
That's right, yeah. It's that same pattern of leaving group attached to the atom that's going to be attacked by a nucleophile. Good. Others? Yeah.
Can you explain just briefly again why the ADP is a good leaving group?
Why the ADP is a good leaving group? Yes. Here it is when it leaves. Its conjugate acid, and I'm going to have to abbreviate it, is this. You add just one hydrogen to one of the oxygens, one proton. This is the monophosphate, the monoanion for a phosphate group. Its pKa is around 7.2. And basically anything whose conjugate acid has a pKa of 16 or less, we're going to say is a decent leaving group. Another way to see it is the negative charge on the phosphate is stabilized by resonance. You may not have thought about this before, but I can push these electrons here and these there, and that shows that the negative charge is actually shared between phosphates. So you got a resonance stabilized anion. Okay, good. Other questions, other hands that I missed? So now you know the kinase reaction for transferring a phosphate group. There's another one of these in glycolysis we're not actually going to pause and go through its mechanism because it would be exactly the same as you've seen here. In fact, let's actually skip ahead to that one. The next kinase step involves adding a phosphate from ATP, the gamma phosphate from ATP, to the C1 hydroxyl of fructose. At this point, you're like, whoa, 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 whoa. We were dealing with glucose. Where did fructose come from? And I'm saying, don't worry about it. We're going to do that in just a minute. But in this next kinase reaction, we're going to transfer the gamma phosphate group from ATP to the C1 hydroxyl of fructose. Via exactly the same mechanism, a base is going to remove the proton on the C1 hydroxyl. That oxygen is going to attack the gamma phosphate of ATP. You'll get that intermediate where phosphate's attached to 5 things. Then the elimination step will happen to kick off ATP. All right. If you want to practice the kinase step offline, you've got the reaction here. Just take a separate sheet of paper, draw it down, and see if you can push your way through it. Remembering that it's all just what we've just done: proton transfer, addition, and elimination. All steps that we learned about last week. All right, other questions about those kinase steps? Let's answer that question from your quiz. Do you expect this reaction to, this reaction is irreversible, it's very downhill. Tell me why. Why isn't anybody going, ain't nothing but a heartache? That's way before your time. You don't even know what I'm saying. You do? Okay, all right. You seen that episode of Brooklyn Nine-Nine? Yeah, it's great. Yeah. Okay, sorry. So tell me why you expect this to be irreversible, downhill. Yes?
Carbon dioxide comes out of it.
So for the whole process, glycolysis, yes. I'm talking about this reaction, step 1. I put an asterisk on it to indicate that it is irreversible and downhill. So why do you think this one's justify that based on the functional groups? Go ahead.
Well, ATP's phosphonhydrides, which are level 1.
Yep.
Phosphorus are level 2, so it's
Going down a level 1 to level 2, level 1 reactive electrophile in ATP to a phosphoester, that's downhill, and it's downhill by a lot. It turns out this reaction doesn't go backwards. It is, and so a glucose molecule is now committed to the process. It can't get out. So this step is highly regulated. Your body doesn't want to do this unless it needs to do it. And if I were a better biochemist, I would tell you something about how that enzyme is regulated, how it gets turned on in order to do its work when your body needs glucose. For now, one of the things you can remember is when a reaction is mostly downhill, that's a step that's likely to be regulated because you can't go back once you've done it. All right. In the last little bit, let's talk about the what that's going on in step 2. This is the third question of your quiz, and I don't think we'll get to this question today. The reaction changes glucose 6-phosphate to fructose 6-phosphate. Let's try to analyze what has changed here. Start by identifying the anomeric carbon in glucose 6-phosphate. Which one is it out of carbons 1 through 6? Which is the anomeric carbon? 1. And you can tell that because it's got an OR group, and which I think I previously colored green, and it's got an OH group. Right? That's a hemiacetal. Now in fructose, which is the anomeric carbon? C1 through C6? C2. It's not C1. Notice C1 is only bonded to one hydroxyl. It's C2 that's bonded to an OR group and an OH group. Bonus question, which anomer of fructose did I draw there? Is that the alpha or the beta anomer? Oh, it's alpha because it's OH is trans to the hydroxymethyl group on C5. So I happen to have drawn the alpha anomer there. But okay. So if we opened up glucose from the cyclic hemiacetal form to the linear form, what would it be? What functional group would it be? Aldehyde or ketone? You can tell it's an aldehyde. How?
Oh, the hydrogen.
Yeah, look at the two things bonded to the hemiacetal carbon that are other than oxygen. If one of them's hydrogen, then it's going to be a it's going to aldehyde. It's going to be an aldehyde. In contrast, fructose, what have you got? 2 carbons, so that's going to be a ketone. Somehow we had to get from a ketone to an aldehyde. Now we're out of time for today, but before you come back next time, I need you to draw forming the open chain form of glucose. I want you to draw a mechanism showing me how the open chain form of glucose forms with the enzyme. I also want you to draw the open chain form of fructose. You don't have to draw the mechanism there, but I need you to do both of those things before we start next time.
Can you send that out in an email?
Will do. Send it out in an email so you can remember. It's also here on the recording because I pressed record.
Yeah, I did see you do
You
that.
did see me do that. All right. See you guys next time.